Today we have the pleasure of having Graham Cox from Memorial University of Newfoundland, who will talk to us about nodal deficiency via equipartitions and Dirichlet-to-Neumann maps. So Graham, thank you very much for being here, and the floor is yours.
All right, thank you for the introduction, and also thank you to the organizers for the opportunity to speak. A lot of people have said this, and I want to echo the sentiment that I've really enjoyed participating in this conference over the last, or this seminar series over the last year. So it's really nice to have the opportunity to give a talk in it. So as the title says, I'm going to be talking about nodal domains of eigenfunctions from a couple of different perspectives. So before I get started, I just want to acknowledge my collaborators. So the new work that I'm talking about today is all joint with Gregory Berkeleiko, Shiza Kanzani, and Jeremy Marzola. And it also ties into some older work that I did with Christopher Jones and Jeremy at UNC. And then there's also some related work, which I'm not going to address here, but kind of ties into all of this, that was done also with Jeremy, Thomas Beck, and then a couple of Jeremy's students, Isabel Bors and Grace Conti at UNC. Okay, so I just want to jump straight into it and introduce some of the basic concepts that I'm going to be talking about. I think this is all pretty familiar to everyone here, so I'm going to go pretty quickly. So I want to start by talking about Courant's nodal domain theorem. So suppose I've got some compact manifold M, and I'm going to assume for simplicity that it's compact without boundary, just to avoid the technicalities that introduces. Now, if I look at the eigenfunctions of the Laplacian on this domain, labeling them starting at 1 rather than 0, as some people do, then Courant's nodal domain theorem, which I think everyone knows well, says that the kth eigenfunction has at most k nodal domains, where the nodal domains are just the connected components of the set where psi k is not equal to 0. So connected sets where it's strictly positive or strictly negative. So if I denote the number of nodal domains by nu, then Courant's theorem just says nu of psi k is less than or equal to k. And then we'll say that an eigenfunction is Courant sharp if it's the kth one and has exactly k nodal domains. In other words, if it saturates this inequality, it has the maximum allowable number of nodal domains according to Courant's inequality. So of course, a natural question is, well, do Courant sharp eigenvalues or eigenfunctions occur? And if so, how common are they? Well, it's not hard to see that the first and second eigenfunction are always Courant sharp with 1 nodal domain and 2 nodal domains respectively. But in general, as is well known, most eigenfunctions do not have this property. So there's this well-known result due to Pleyel, which says, if I look at this ratio of nu divided by k, so by Courant's theorem, this is always less than or equal to 1. Well, asymptotically for large k, this is actually bounded above by some constant, which is strictly less than 1. And so that means once k is large enough, nu is always strictly less than k. And so on any given domain, there can only be finitely many values of k for which this ratio is equal to 1, i.e. only finitely many Courant sharp eigenfunctions on any given domain. Okay, so you could then ask, well, even though there are only finitely many Courant sharp eigenfunctions, then you'd like to characterize them or know when they occur, when they don't occur. And so there are lots of examples where people have found all of these explicitly. So things like the square, the torus, ball, triangle, etc. So there are a lot of results here. I'm not going to go through them explicitly. But the thing you'll notice here is that these are all very nice symmetric domains where things like separation of variables apply and things can be computed very explicitly. In terms of more general results, there are also some nice upper bounds on the maximal number of Courant sharp eigenfunctions that any given domain can have. Right? So of course, for a given domain, there can only be finitely many, but you might ask, well, how big can that finite number be? in terms of some invariant geometric quantities of the domain. So there's some nice results along those lines due to Berard and Helfer and Vandenberg and Gittins, amongst others. Okay, so this says that, well, Courant's theorem gives an upper bound on the number of nodal domains. It's generally a strict inequality. So as far as upper bounds go, it's not really the most satisfactory thing. And in terms of a lower bound, the situation is similarly bad. So, well, you know that every eigenfunction beyond the first one has to have at least two nodal domains. It has to change sign somewhere. It turns out that you can find lots of examples of eigenfunctions with arbitrarily large k, so corresponding to eigenvalues arbitrarily far along in the spectrum, but having only two or three nodal domains. So examples like this exist on the square, the sphere. Also more recently, some work of Jung and Zeldich constructed similar counterexamples or examples on a particular class of three manifolds called Kluser-Klein threefolds. So this shows that, well, the number of nodal domains has to be somewhere between 2 and k. It can take on pretty much any value in that range. And again, in terms of these examples here, I'm not going to say anything more about them, but you'll similarly notice that these are all very symmetric examples. So there's a lot of geometric structure used in constructing these counterexamples. Now, in terms of talking about number of nodal domains, I'm not going to talk about the number of nodal domains nu directly. Instead, it's more convenient to work with a quantity called the nodal deficiency. So this is, for the kth eigenfunction, it's just k minus nu. And so Courant's theorem says that this is greater than or equal to 0. And so in general, we would like to know how big or how small this is and what it tells us about the geometry of the eigenfunction psi k and its nodal set. So that's a very quick overview of nodal domains and nodal deficiency. I think this is all pretty familiar to this audience. And so the general summary here is that nodal deficiency of eigenfunctions is a very interesting quantity to look at, but also a very difficult and very intractable one. Okay, so that's a very brief overview. Now, what am I actually going to talk about today? Well, first, I'm going to start off by summarizing two relatively recent formulas that were given for computing nodal deficiency of eigenfunctions. So the first one is a result due to Berkeleiko, Kuchment, and Smilansky from 2012, where they compute the nodal deficiency of Laplacian eigenfunctions using something called the equipartition energy functional. Next, I'm going to review a more recent result that I proved with Chris Jones and Jeremy Marzola, where we compute nodal deficiency using Dirichlet-to-Neumann maps defined on the nodal set of the eigenfunction. And after reviewing these two approaches, I'm going to talk about some new work joint with Gregory Berkeleiko, Shaiza Kanzani, and Jeremy Marzola, which explains how these first two approaches are connected. So we'll see actually a very explicit, very satisfying relationship between this equipartition energy functional and the Dirichlet-to-Neumann maps defined on the nodal set of the eigenfunction. So to introduce the work of Berkeleiko, Kuchment, and Smilansky, first I want to say a little bit about spectral minimal partitions. So if I have some k partition of my domain M, remember I'm going to assume throughout that M is just some compact manifold without boundary, then I can define this quantity lambda of p where I just look at the first Dirichlet eigenvalue on each component of the partition and then maximize. So it's just the largest ground state energy for for all of the components of this partition. So this is a well-defined quantity. And I'll say that this partition P is a spectral minimal partition if it achieves the minimum of this lambda. Now, spectral minimal partitions have been studied a lot. So there's a lot known about them. I'm going to give a very brief summary of some of the results. This is certainly not everything that's known, but just the pieces that are most relevant for what I want to talk about today. So first off, it's known that for any value of k, a minimal k partition exists. It also has some nice regularity properties. So in the planar case, the boundary of the partition has to consist of a collection of smooth curves, except for some finite number of exceptional points where these curves intersect. And at these points where they intersect, they always do so at equal angles. So this is a property that is well known for nodal sets of Laplacian eigenfunctions. Another nice property that these minimal partitions have is that they are what are called equipartitions. I'll elaborate on this on the next slide, but basically what that means is that the first Dirichlet eigenvalue on the component omega j is actually independent of j. So each piece of the partition has the same first Dirichlet eigenvalue. And finally, a really nice result says that if we have a minimal partition that is also bipartite, that basically means you can color all of the components in the partition, say into red or blue or black and white or positive and negative, so that any two adjacent pieces of the partition have different colors. So if I have a bipartite minimal partition, then in fact, it is the nodal partition of a Courant-Sharp eigenfunction, meaning the omega j's are just the nodal domains of that eigenfunction, and it's a Courant-Sharp eigenfunction, meaning it has the largest possible number of nodal domains. So this is a very quick review of some results that are known about spectral minimal partitions, and there's a lot of really nice work here, and in general, these are very hard, very technical results to prove. And the reason for that, I think, is because a priori, these partitions are not assumed to have much in the way of regularity or smoothness, so that makes their analysis quite involved. Another thing, which from the optimization point of view is very relevant, is if you look at this function that you're trying to optimize, well, of course, it'd be natural to try to use methods from the calculus of variations, but this lambda of p is unfortunately not a smooth function. The reason for this is not particularly subtle. It's exactly due to this maximum here. So imagine taking a partition. If you deform all of the components of the partition in a nice smooth way, well, each of these eigenvalues is going to change smoothly in terms of that deformation. But then when I take the maximum of a bunch of smooth functions, I'm going to get something which is at best Lipschitz. So the lack of smoothness makes the analysis a lot harder here. However, a really nice observation is that if instead of looking at the set of all partitions of our manifold M, we restrict attention to the space of equipartitions, then that smoothness problem is no longer there. So why is that? Well, remember the lack of smoothness here was just due to the fact that I was taking a maximum of a bunch of different things. Well, for an equipartition, all of these numbers are the same. And so the maximum is just equal to any one of these numbers. And those all change smoothly when the partition is deformed. So just to state formally, what is an equipartition? Well, it's just some partition of our manifold M with the property that the first Dirichlet eigenvalue of each component omega j is the same. So this lambda 1 of omega j actually doesn't depend on j.
Excuse me, Graham.
Yep.
Alex here. Are you saying that if you start with the equipartition, you can deform it in a way that it remains equipartition?
That's correct. And actually, I think the very next thing I'm about to say will address that a little bit more precisely.
Okay, thank you.
Yeah, so what Berkolayko, Kuchman, and Smolansky observed is that if we take a smooth equipartition, so I mean, by smooth, I mean that the boundaries of all of the components of the partition are smooth. In particular, there are no intersections allowed in this case. Then the set of all equipartitions, or at least all nearby equipartitions, can actually be given the structure of a smooth Hilbert manifold. And if we look at this function lambda, which is just this energy functional restricted to the space of equipartitions, then that becomes smooth. So in terms of the set of all partitions, the space of equipartitions is just going to be some submanifold. And if you think about it, suppose I'm talking about a K partition, so I've got K different components. The condition that that be an equipartition, so all K of those ground state energies are the same, that imposes exactly K minus 1 conditions. So the set of equipartitions is going to be a submanifold of codimension K minus 1 in the set of all smooth partitions. So does that answer your question, Alex?
I think so. I'm just surprised that they can all be smooth, the pieces, but
well, I mean, this is assuming that P is a smooth equipartition. So for instance, if you had something like this on the square, well, this is not allowed here. So we're only talking, for now, I'm only talking about things where all of the boundaries are smooth, and then nearby things are going to be small deformations of that, which are all smooth as well. So there's no kind of discontinuity or lack of smoothness in the nodal set, which is allowed so far.
Great, thank you.
Yeah, no problem. All right, and so I'm not going to say anything about the construction here, but the idea is, well, if you think about deforming your partition, so just moving it by some diffeomorphism, well, you can parameterize these deformations using vector fields defined along the nodal set or along the boundary of the partition. And well, in terms of deforming the domain, you really only need a normal deformation. Tangential deformations don't actually move the partition at all. And so we can parameterize these deformations by normal vector fields defined along the nodal set. And they'll be of some smoothness, say in some Sobolev space HS for sufficiently large S. Okay, so now we have this manifold of equipartitions. It's a nice smooth manifold, and I've got a smooth energy functional defined on it. So now I can talk about critical points, minimizers, saddle points, everything like that. So the first thing to do is understand what critical points look like. So again, I'm going to take some smooth equipartition, and on each omega j, I'm going to let psi j denote the ground state, meaning the first Dirichlet eigenfunction, and I'll assume that it's normalized on omega j. Now, if this partition was actually the nodal partition for some eigenfunction, well, then the first Dirichlet eigenfunction on each omega j is just the restriction of psi to that domain. And so that means on each domain, psi j is proportional to the restriction of our original eigenfunction psi. And the constant of proportionality here just comes from the normalization. So what this says is, well, if you have a nodal partition for an eigenfunction, then all of these ground states psi j actually fit together in a nice way to form a smooth function psi defined on the entire manifold M. And it turns out the converse to that is true exactly when you're at a critical point of this functional lambda. So in particular, this partition, again, this is with all the smoothness assumptions that I was imposing before, a partition will be a critical point in this lambda if and only if there exists some constants aj, so that if I look at this weighted combination of all of the ground states, psi j, then it has the property that every time I have two intersecting partitions, say here's omega I and omega j, if I look at the normal derivative, say coming from the omega I side or the omega j side, the normal derivatives agree up to a sign. So my convention here is that nu is always going to be the outward unit normal. So say this would be nu I and nu j pointing in the opposite direction. So if psi was actually a continuous function, say, if its normal derivative was continuous, then these would be equal to minus one another. Now, but in general, this is just saying the absolute value of the normal derivative is continuous along all of these interfaces. So in particular, if I fix two different domains, say omega I and omega j, that share some boundary component, well, if I go back to this formula here, notice that this condition here, it's on the absolute values, and so the sign of the aj is irrelevant here. So if I take two adjacent nodal domains, omega I and omega j, I can always flip the sign on either ai or aj to guarantee that their normal derivatives are equal but opposite along that interface. And so that means this function psi is actually going to be smooth across that boundary. And hence, it's actually an eigenfunction on the union of the two, omega I union omega j. And so this is exactly what is called the pair compatibility condition in this minimal partition literature. Now, this is just for two adjacent partitions. I can always make this true by just swapping the sign on either ai or aj. In general, the condition, I can't guarantee that this is possible globally, except in the case that P is bipartite. If it's bipartite, that exactly tells us that we can choose these AJs consistently across the entire partition to ensure that this matching condition holds on every single boundary, on every single intersection of boundary of omega I and omega j. And so what that means is that this function psi that I've constructed, its normal derivative is actually continuous across all these boundaries. So it actually gives an eigenfunction on all of n. In other words, this is just the result that a smooth bipartite equipartition is critical exactly when it's the nodal partition of some eigenfunction. But again, this result is a little bit more general. It also says something non-trivial in the non-bipartite case, just giving this pair compatibility condition. Okay, so those are critical points of this energy functional. Now, where we're really starting to get into nodal deficiency is when we talk about the Hessian of this. So let's suppose I have a generic eigenfunction of the Laplacian. So by that, I mean one corresponding to a simple eigenvalue and having a smooth nodal set. So it's well known by a result of Uhlenbeck that Laplacian eigenfunctions for a generic metric will have this property. So then the nodal, sorry, this should say nodal partition, not nodal set. The nodal partition generated by this eigenfunction is going to be a smooth bipartite equipartition. And so it automatically gives a critical point of this energy functional lambda. And then the main result in this paper of Berkolayko, Kuchman, and Smolansky from 2012 is that for a generic eigenfunction, the Hessian of this energy functional evaluated at its nodal partition is non-degenerate, and its Morse index is exactly equal to the nodal deficiency of the eigenfunction psi in question.
Graham, can I ask a question again?
Yeah, of course.
When you say generic, you mean with respect to a change of the Riemannian metric, or do you mean?
That's right. So I'm using generic just to mean an eigenfunction with these properties that are generically true. So by generic here, I mean simple and having us say 0 as a regular value. So it's a smooth nodal set. So when I say generic, that's really what I mean. But I'm kind of implicitly relying on this theorem of Uhlenbeck's, which says for a generic Riemannian metric, all of the Laplace-Beltrami eigenfunctions will have these properties. All right, so yeah, so this is their theorem. It says the Hessian is non-degenerate and its Morse index is exactly computing the nodal deficiency of the eigenfunction. So this is a really nice result, and to the best of my knowledge, this formula, which was proved or at least published in 2012, is the first explicit general formula given for the nodal deficiency. So in particular, if we look at local minima, well, a local minima is exactly a critical point with Morse index equal to 0. Then this says that, at least in this smooth setting, a bipartite local minima of this function is exactly the nodal partition corresponding to some Courant-Sharp eigenfunction. And so similarly, if we have some smooth bipartite critical point, which is a saddle point but not minima, then it's going to be the nodal partition of some eigenfunction which is not Courant-Sharp. And this result can actually be generalized a little bit. If we allow the eigenvalue to have multiplicity m, but still assume that it has smooth nodal set, then a slight generalization of this theorem holds. The Morse index of the Hessian will still be the nodal deficiency. The Hessian will no longer be non-degenerate. It will have nullity or degeneracy exactly equal to m-1. So basically, all of the other m-1 eigenfunctions, in addition to this psi, are going to give degenerate variations, degenerate directions in the Hessian. Okay, so one last thing before I move on to Dirichlet-to-Neumann maps. I just want to remind you of when I say Morse index, what do I mean? And this is going to be important later on when I talk about the connection between this approach and the Dirichlet-to-Neumann map approach. So notice that the Hessian of lambda by construction is a bilinear form, and it's acting on the tangent space to this manifold of equipartitions. So the Morse index is just the maximal dimension of some subspace U in the tangent space to this manifold of partitions on which the Hessian is negative definite. Okay, so that's the case for smooth partitions. What we're going to see later on, and I'm only going to touch on this very briefly at the end, if we look at non-smooth partitions, so that means allowing for things which have, say, intersections in their nodal sets, which certainly can happen, in that case, it turns out, well, the Hessian is still going to be well defined in that case. The tangent space there is simply not big enough to capture the entire nodal deficiency. And so in the non-smooth case, it's going to turn out that the Morse index of the Hessian, defined in this way, is actually strictly less than the nodal deficiency. There's somehow going to be additional contributions to the nodal deficiency, which are not coming from nice smooth tangent directions in the space of partitions. But I'll say more about that later on. But again, just before I go on, I want to emphasize that the Hessian here is not an operator. It's a bilinear form defined on the tangent space. And so if I want to associate that to an operator, then I need to pick some inner product on the tangent space. So we'll see this all a little bit later on. Okay, so that's the equipartition approach to nodal deficiency. Now I want to talk about the work that I did with Chris Jones and Jeremy Marzola, where we gave a different formula for nodal deficiency in terms of the Dirichlet-to-Neumann map. So I'm just going to take some eigenfunction psi with eigenvalue lambda and take my manifold M and decompose it into two pieces, omega plus and omega minus, just the set of all points where psi is positive or negative, respectively. Now, if I look at the nodal set, so just the set of all zeros of my eigenfunction inside the domain, what I'm going to do is define Dirichlet-to-Neumann operators lambda plus and lambda minus on this nodal set, somehow in terms of these positive and negative sets, omega plus and omega minus. And in doing that, I'm going to need to be a little bit careful because lambda, which was the eigenvalue of the eigenfunction m or psi that I started with, basically by construction, lambda is an eigenvalue for the Dirichlet Laplacian on these sets omega plus and omega minus. And so I need to take that into account when I define these Dirichlet-to-Neumann maps. So to do that, I'm going to define some set S of all functions. This would be, say, functions on sigma that are orthogonal to the normal derivative of my eigenfunction psi. So this is just going to give some, this is just the orthogonal complement of the normal derivative of psi. And this is going to correspond to a solvability condition for a boundary value problem. So in particular, if I take some function f on the boundary that satisfies that constraint, then this boundary value problem, Laplacian u plus lambda u in omega plus with boundary condition equal to f, is guaranteed to have a solution. So this is only true if f satisfies this orthogonality condition f. F is in S. So that's why I needed that. Okay, so this boundary value problem has some solution u. Now what I'm going to do is take its normal derivative using the outward unit normal to omega plus, evaluate the normal derivative on the boundary. So this is some function on the nodal set sigma. And then I'm going to follow that by the orthogonal projection onto this subspace S. So this is what I'm calling lambda plus, the Dirichlet-to-Neumann map on the domain omega plus. And I have to be a little bit careful here, of course, because, well, f being in S guarantees that this boundary value problem has a solution. It's certainly not unique. I could just add any multiple of psi to u and get another solution. But if you work it out, well, if I have another solution u tilde to the boundary value problem, well, as I just said, it only differs from any other solution u by some multiple of this eigenfunction psi. So if I work out its normal derivative and then apply this projection, what we'll see is this extra term here just gives me the normal derivative of psi. Now pi is exactly projection away from the normal derivative of psi. So this term is guaranteed to be 0. And so that tells me that this lambda plus is well defined. It doesn't matter which solution to this boundary value problem I choose. Lambda plus of f is independent of that choice. So that's lambda plus, where I solve this differential equation in omega plus. If I do exactly the same thing, replacing omega plus with omega minus, then I'll get my other Dirichlet-to-Neumann map, lambda minus. And then the theorem that I proved with Jones and Marzola says that under some regularity condition, namely that all of the nodal domains have Lipschitz boundary, then the Morse index, or number of negative eigenvalues of lambda plus plus lambda minus, this is what I'll call the two-sided Dirichlet-to-Neumann map, the number of negative eigenvalues is exactly equal to the nodal deficiency of the eigenfunction psi that I started with. And also the number of 0 eigenvalues is just equal to m minus 1, where m is the multiplicity of the eigenvalue associated to psi. So in particular, if it's simple, then this tells us that it's non-degenerate.
But do you allow intersections here?
Yeah, in this case, intersections are allowed as long as, if you had something like this, which has intersections, each one of the nodal domains has Lipschitz boundary, and that's all we need for this argument to hold.
Thanks.
Yep. So, yeah, so this is actually, compared to the equipartition approach, the regularity assumptions are a lot weaker here. The original proof we obtained using the Maslov index. So this is using some infinite dimensional symplectic linear algebra. Another proof, I think a much simpler one and probably more natural to people in this seminar, was given a few years later by myself also with Greg and Jeremy. There we use the spectral flow for some family of self-adjoint operators. So that gives a different, I think maybe more natural proof of this result. And this spectral flow approach was actually very recently generalized to equipartitions that are not necessarily bipartite, so non-nodal equipartitions, as long as they satisfy this pair compatibility condition. This was done by Helfer and Sundqvist just over the summer, I believe. Okay, so one thing I want to do now is, if I look at this lambda plus lambda minus, so what I'm calling the two-sided Dirichlet-to-Neumann map, I can rewrite this as just the sum of lambda j, where lambda j is just the Dirichlet-to-Neumann map on omega j. So these are just kind of trivially the same thing. But the reason why I want to do this is if I have any partition omega into omega j's, the right-hand side makes sense. The left-hand side only makes sense for a bipartite partition or a nodal partition where we can divide it into positive and negative components. So for the rest of the talk, or for most of it, when I'm talking about general partitions, I'm just going to talk about the sum of all of the lambda j's instead of lambda plus and lambda minus. Okay, so let's just kind of take a break and see where we are so far. So what I've done is review these two different approaches to nodal deficiency, one through this equipartition energy, and one using Dirichlet-to-Neumann maps. And comparing them, what we find immediately is that as long as we assume the nodal set is smooth, well, the Morse index of the Hessian of this equipartition energy functional is equal to the Morse index of this two-sided Dirichlet-to-Neumann map. And well, this holds immediately because both quantities are equal to the nodal deficiency of the eigenfunction psi, and so they have to be equal to one another. So, I mean, that tells us these quantities are equal, but it's not a very satisfying argument. It doesn't actually give any explanation as to why these are the same quantity. And so the question that I want to address is, can we actually relate these operators directly, or really this operator and the Hessian, which is a bilinear form? In the smooth case, can I come up with a direct connection between these operators? And then can I generalize that to the non-smooth case? And either way, what is this correspondence going to tell us about nodal deficiency and spectral minimal partitions? So the answer to question one is yes, there's a very explicit correspondence here. So in particular, what we were able to show is that if I have a smooth critical equipartition, doesn't need to be bipartite, then the Hessian of this energy functional, this bilinear form, in a natural way corresponds to a self-adjoint operator that is similar to the sum of all of the Dirichlet-to-Neumann maps on the different omega j's in the partition. So what this tells us is that whatever this self-adjoint operator corresponding to the Hessian, well, it's similar to the sum of the Dirichlet-to-Neumann maps. So it has exactly the same eigenvalues up to this factor of 2. And so we immediately recover this result that the Hessian and the two-sided Dirichlet-to-Neumann map have the same Morse index. But of course, this is a lot more satisfying because we see exactly where this equality is coming from now. And we get even more. So the similarity transformation between these two operators, it turns out, is just multiplication or division by the normal derivative of this ground state psi, which generates the equipartition. And so what this means is if we know the eigenfunctions for the two-sided Dirichlet-to-Neumann map, then that immediately tells us the eigenfunctions for the Hessian, just dividing by the normal derivative of psi here. So why is this true? Well, I'm not going to go through all of the details, but at the heart of it is the following result, which is essentially just a calculation, but it has some nice geometric ideas in it. So the point is, if I have some smooth critical equipartition P, now if I imagine varying that equipartition by varying along some vector field X, which is tangent to the space of equipartitions. So I'm considering a variation within the family of equipartitions generated by X, then the Hessian of the equipartition energy in the X direction is given by this explicit formula. And so you see here that, well, here's the normal part of the vector field generating the deformation. Here's the normal derivative of the function psi, which is generating this equipartition. And then here's the Dirichlet-to-Neumann map for the jth component. And so I just get this summed over all j's. Okay, so I want to really quickly say the idea of the proof here. And the idea is, well, let's look at a single domain omega j first and calculate the Hessian, or second derivative, of the first Dirichlet eigenvalue, lambda 1 of j. So this is a calculation that's been done before. You can look this up. It's in papers and books. And it's a pretty messy formula in general. But if you look at it, what you'll see is it has the following form. So the first term is going to involve some function u times its normal derivative, where u solves some inhomogeneous boundary value problem, plus what I'm calling odd terms. And I'll comment on those on the next slide. Now, if I look at this first term, u times du d nu, well, u on the boundary is just equal to minus this quantity here. That becomes this expression. On the other hand, the normal derivative of u is just equal to the Dirichlet-to-Neumann map applied to the Dirichlet data of u. And so I get this formula for the Hessian. This is just on a single domain omega j still. So this first term already looks pretty close to the answer that I claimed before, plus these mysterious odd terms. Now, what do I mean by odd terms? Well, these are just geometric terms on the boundary that are going to depend on the orientation of the normal vector. So remember, if I had some, say, omega I and omega j, well, on any shared boundary, the normal derivatives, the outward normals to omega I and omega j, are equal but opposite. And so in particular, quantities like the mean curvature, if I look at the mean curvature of this viewed as the boundary of omega I, it's exactly minus the mean curvature of this same thing viewed as the boundary of omega j, because the mean curvature depends on the normal direction. And so what happens now is I've calculated the Hessian of an eigenvalue on a single nodal domain omega j, but because I'm looking at an equipartition and a variation within the family of equipartitions, this is actually independent of the choice of j. So if I computed this for any other omega j in the partition, I would get exactly the same answer. And so what that means is if I just add all of these things together or take some weighted average of them, it's going to give me the same thing. So what I do is just add these up over all of the omega j's. I'm going to take some weighted average using these aj coefficients, and skipping all the details because I don't have much time left. This weighted sum is constructed in such a way that all of these odd terms on the boundary exactly cancel out, because each one is going to show up twice, say on the boundary of omega j and the boundary of omega I, with opposite signs. So these all cancel, and I'm just left with this term, which very explicitly involves the Dirichlet-to-Neumann map. So that's the proof of that lemma. Now, just to simplify things a little bit, what I want to do is let's pick some unit normal nu everywhere on the nodal set sigma. So on each component is going to be plus or minus nu j, doesn't matter which one, just pick anything. And now if I look at the Hessian, just for some normal variation, so given by some function psi times this normal nu, then the calculation that I had above reduces to this slightly nicer looking formula. The important thing here is, I mean, this is trivial, but the thing to notice is that in this formula here, notice that nu j shows up exactly 4 times. And so on each boundary, whether this normal nu that I choose is plus or minus nu j isn't going to make a difference because it shows up an even number of times. Okay, so now I have an explicit formula for this Hessian bilinear form. The Dirichlet-to-Neumann map shows up very explicitly. And so now I just need to think about finding a self-adjoint operator corresponding to this. So if I'm still working in the generic case, well, the normal derivative of psi, this term here, is never 0. It's bounded away from 0. From that, I can see that this Hessian actually is going to give me a closable bilinear form just on L2. So I can actually extend its domain to get a bilinear form on L2 with form domain h1/2, just using standard representation theorem for self-adjoint operators. And it gives me a self-adjoint operator of this form, which you can see right away is congruent to the sum of Dirichlet-to-Neumann maps. And so since it's congruent, that says it has the same Morse index as the sum of the lambda j's. However, this isn't quite what I wanted because, well, this is giving me a congruent operator and hence one with the same index. It doesn't actually tell me any relationship between the eigenvalues or the eigenfunctions. And it also relied on the assumption that the normal derivative was non-zero, which in the case of intersections is no longer going to be true. And so what we can do instead is look at this weighted L2 inner product. So I'm going to view the Hessian as a bilinear form and then use it to construct a self-adjoint operator with respect to this weighted L2. And then when I do that, this is the resulting operator that I get. And so we see explicitly that it's similar to the sum of all of the lambda j's. And the similarity transformation is just multiplication or division, depending on which way you're going, by the normal derivative of psi. So that basically proves the theorem that I stated. So I know I'm just about out of time. I want to take the last few minutes to go through a concrete example just to show how we can use this construction to explicitly find eigenfunctions for this equipartition energy functional in a really simple case where everything can just be done by hand. So I'm going to look on this unit square and consider, say, the 3-1 mode, so just this eigenfunction here. And so if you just do the numerology, what you'll see is this is the 5th eigen. It corresponds to the 5th eigenvalue, and it has 3 nodal domains. So that means its nodal deficiency is 2, meaning the Hessian should have exactly 2 negative eigenvalues. And it has multiplicity 2, because there's also the corresponding 1-3 mode. And so that means the nullity should be equal to 1. So the Hessian should have 2 negative eigenvalues and 1 0 eigenvalue. In this case, you just separate variables. You can explicitly find these are the first 3 Hessian eigenfunctions. And I've written them in terms of increasing eigenvalue. So this is the most negative eigenvalue. This is for the other negative eigenvalue. And F3 corresponds to the 0 eigenvalue of the Hessian. Now I just pick some normal direction. I'll just make it pointing to the right everywhere here. Do the similarity transformation, divide by the normal derivative. And what I get are the corresponding eigenfunctions for the Hessian, or really for this self-adjoint operator that corresponds to the Hessian. So these are the explicit formulas for them, just simple calculation. And then these figures show what happens when I take this simple nodal partition here and perturb it in the direction of any of these eigenfunctions. So again, this is the perturbation corresponding to the most negative eigenvalue. This is the other negative eigenvalue, and this is the zero eigenvalue. So what does this say geometrically? Well, let's look at phi3 first. That's the simplest one. Well, if you stare at it for a second, you'll realize that this is exactly, this deformation just corresponds to moving through this one parameter family of eigenfunctions, just taking linear combinations of the 3-1 and 1-3 mode. Right? We know that this is a degenerate eigenfunction. So we've got this one parameter family. Moving along this is going to give us something in the kernel of the Hessian, and that's exactly this one here. On the other hand, let's look at phi1. So this is the eigenfunction corresponding to the most negative eigenvalue. So here's the original partition we started with. Here's its deformation in the phi1 direction. And this, I mean, this is very heuristic, but as you do this deformation more and more, you'll see that things are moving in here and sort of pinching off, whereas they're moving out up here. And so you might conjecture that this should be converging in some sense if you keep flowing in this negative direction towards something which looks like this. And this shape is exactly the conjectured minimal 3 partition on the square. So this doesn't prove anything, of course, but I think it's a really nice picture and shows that deforming along the most negative eigenfunction seems to be moving in the direction of what is conjectured to be the minimal 3 partition. So that's everything for the smooth case. We have some preliminary results in the non-smooth case, but it's still work in progress. I think I'm out of time, so maybe I'll skip over that. So just to really quickly summarize, hopefully I've convinced you that nodal deficiency is an interesting but very difficult quantity to study. There previously were 2 different approaches known for computing nodal deficiency, using these equipartitions or using the Dirichlet-to-Neumann map. And what I've shown today is that these are really actually exactly the same thing, or they're very explicitly related to one another. And then using this correspondence, we can pull out information about eigenfunctions of the Hessian of this equipartition energy, which we should then be able to use to say things about minimal partitions and nodal partitions in general. So I'll stop there, and thank you for your time.
Thank you very much, Graham, for your talk. Now is a good time for questions. If anybody wants to go ahead, do.
I have a silly remark. This is Dima Jacobson. I think maybe one of the simplest examples of functions with exactly 2 nodal domains on the 2 torus is sine of, in brackets, n times x minus y for all n. And nodal domain kind of 2 nodal domains snake around the torus and close back on themselves. So it could be interesting to compute, to make a similar computation to what you did at the end in that example, just to see. So this would be perhaps, the maximally degenerate case or something. It's much easier than the examples on this. It's a bit easier than examples on the sphere.
Yeah, that's a good point. I haven't tried computing anything for that example explicitly yet. So
yeah. So and it's also easier with this, yin and yang example, example of 2 nodal domains in the square in like Korn-Hilbert or whatever. And another question is kind of naive, but so you were saying that the functional, which is if you have a partition, you take the sum of the maximum of the first Dirichlet eigenvalues, and that's non-smooth because maximum is non-smooth. right? So I was thinking about relaxation. So suppose you could take, instead of maximum, you could take the sum of Dirichlet eigenvalues to whatever to the power p and take the pth root, right? And then if you let p go to infinity, you'll get the maximum. It's easy to show, but that guy should be nicer, smoother. But on the other hand, I don't know if it's interesting to look at this functional and what will you get. Not
there
sure.
is a simpler answer to this. Actually, this functional is non-smooth, but you can define Morse index for non-smooth functional essentially through subspaces of decay, and then this non-smoothness of this functional doesn't hurt at all, since all non-smooth directions lead to increase.
Okay.
So essentially, one can kill equipartition condition, and the same is true for non-smooth maximum. But it doesn't add anything.
Okay.
May I ask a question?
Yes, go ahead.
My question is the following. I don't know, I know about Maslov index from classical mechanics. And there you can show that it is indeed the Morse index of some action functional of paths. Now, my question is, can you explain to me what you said in some point of your lecture about the connection that you see between the Maslov index and the deficiency?
Sure. So yeah, this is some work that I did with Chris Jones and Jeremy Marzola a few years ago, where we were using the Maslov index to count eigenvalues for Laplacian or other self-adjoint operators. And the idea in our setup is you have two Lagrangian subspaces where essentially one encodes the solutions to your differential equation, and the second subspace corresponds to the boundary conditions. And so then intersections between these two subspaces is measured by the Maslov index. And that's exactly counting solutions to your boundary value problem. And so essentially what we were doing is looking at, take a domain and decompose it into two pieces, say omega plus and omega minus, look at boundary data on the interface between those, the nodal set, and then the Maslov index is essentially counting when you have solutions on omega plus and omega minus, which coincide on the nodal set, meaning they actually extend to smooth solutions on the entire manifold M.
Thank you.
So Bernard Elfer
Yes,
you have a question?
I have various comments. First, to the question between the L infinity consideration or LP configuration. I have two remarks. First, this technique appears in the proof in a paper with Susanna Tiracci and Thomas Hoffman also, that we go through a more regular version. I'm considering also the P, the partition corresponding to powers of the lambda G to the power P. The other point is that minimal partitions for this other functional are not equipartitions. So you lose the property that a minimal partition, when you consider the P powers of the eigenvalue, you lose the equipartition property. So I don't know. I have another question about how do you define a regular deformation? Because you have a nodal structure with corners and so on. So what is the condition on your vector field in order to define this deformation?
That's a very good question. And that's, I mean, this is the part right towards the end of the talk that I kind of skipped over because I was running out of time. But so in the, I mean, the first result that I mentioned, the Berkolayko, Kuchman, Smolansky, Equipartitions, that, I mean, that result is just for smooth equipartitions. So as in that setting, there are no corners.
Okay, so do you mean each nodal domain is smooth? Each nodal boundary is smooth.
That's
no
right.
Crossing, no crossing. Okay.
No, that's right. So that in their work, they assume no crossings. And then you can just parameterize deformations by, say, you have normal vector fields along
okay.
the nodal set.
In this case, I understand, but in the case of corners, it's less clear in the sense that the way you define the vector field, the condition that you can put on the vector field.
Yeah, so that's what we're working on now, and the geometry is certainly more subtle because, right, it doesn't make sense to talk about a normal deformation of the nodal set when you've got an intersection. So we're working on that now, and I think we have an approach to
okay, but if you
parameterizing at least smooth deformations in the neighborhood of a corner.
If you consider only this smooth case, deep psi over d nu is naturally not zero by Hopf theorem, or if the restriction of psi to the nodal domain is the ground state. Deep psi over d nu should not vanish.
Yeah, that's right. In the generic smooth case, the normal derivative is never zero, and that's
okay. Thank you.
Yeah.
But about parameterization, it seems to me that the natural way to parameterize, which is equivalent to vector field and only in smooth non-intersecting case, is to parameterize by diffeomorphisms.
Yes. Okay.
Yeah, that's the approach we're working on now. We're essentially, yeah, you can imagine diffeomorphisms on acting on your entire manifold, and then you quotient out by all of the ones that are not actually moving the nodal set, and that should give you a parameterization of at least smooth deformations of the nodal set, even in the case that you have intersections.
Thank you. Anyone else has questions or comments?
Graham, since you already told us a lot about that previous slide, could you maybe give us the full thing?
So about for the non-smooth case, you mean?
Yeah, I feel like you've told us already like half of it at least.
Yeah,
so maybe it wouldn't take too long.
So I mean, this is a pretty vague slide, but I can say really quickly, what we're doing is looking at, so consider a nodal set that maybe has some intersections in it, so it's not smooth. What we're doing is looking at smooth deformations of that, by which I mean take this partition and act on it by some diffeomorphism in HS, say, for a big enough value of S. So that might move around this intersection point or add some oscillations to your nodal set, but it's not going to change the topology or break it apart or anything. And yeah, so essentially through this approach of just looking at HS diffeomorphisms, moving, acting on the space, modded out by the ones that fix the nodal set, then that gives us a smooth structure, at least on the set of nearby partitions. Nearby meaning something like this. And then it seems like all the calculations that I talked about go through with, there's some more technical details to check, but basically without modification, the same conclusion is true. But the really interesting thing that happens here is when I construct this self-adjoint operator that's corresponding to the Hessian bilinear form, remember that I'm using this weighted L2 space where my weight is the normal derivative of psi. And now in the case of an intersection, well, the normal derivative is definitely going to vanish at this intersection point. And so that means functions in this weighted space could actually blow up at some certain rate at this intersection. And in some, so that means we get this self-adjoint operator corresponding to the Hessian. Some of its eigenfunctions are going to correspond to variations that are actually not smooth and don't even stay within this nice manifold of partitions as we currently understand it. I mean, they're going to be exactly the things that will take this cross and resolve it into something like that. But actually precisely describing the structure of the space of partitions, in a neighborhood of these 2 points is still something that is ongoing. So I think, yeah, short answer is kind of smooth deformations of non-smooth things we can handle. Non-smooth deformations of non-smooth things is still very much a work in progress.
Thank you.
You, Misha, anyone else has a comment or question?
I would have one, yes. So when you showed us the example for the square, where you had this convergence for the lowest eigenvalue of the Hessian to this, this conjectural convergence to the minimal 3 partition for the square. Is this phenomenon something that you see numerically in other examples, or is this the only example where you've seen this phenomenon?
I would say honestly, we haven't done that many really explicit examples yet to check. So this is kind of, this is the simplest, most concrete example I've done so far. I was going to do the similar calculation for 3 partitions on the disk, but I haven't finished that calculation yet. But we'll see what happens in that case.
I guess I'm asking because normally I feel that in this kind of problems where you use a flow to converge to some minimal object, the hardest part is showing existence of the limit object, but we already have existence from what you've talked about at the beginning for these minimal K partitions. So intuitively it seems to me that what I would think would be the hardest part is achieved in a way, right?
Well, there's a subtle, or maybe not so subtle, but there's a hard thing that needs to be addressed, which is, even if the limit is already, as you said, the limit is already known, or it's kind of, you have a guess of what the limit is, which certainly helps. In this case, though, I think the hard thing is what's happening between the starting point and the ending point. In particular, right, the topology of this partition has to change at some point.
Yeah,
these 2 lines are getting closer together, and then somehow they're going to intersect, and right, it goes from being smooth and bipartite to non-smooth and non-bipartite somewhere along the way. And so, currently we can kind of understand variations around things like this and variations around things like this, but not variations that connect the 2 together. And right, in Peter's talk a couple weeks ago, he was talking about the space of all partitions, and the kind of the belief or the heuristic view is that it has some sort of stratified structure. So you've got different smooth pieces of the set of all partitions that are fitting together, hopefully in some nice regular way. And so this flow would actually be going between 2 different strata in this space, and that's.
Oh yeah.
So there's going to be, that's certainly going to be a non-trivial thing to understand.
Thank you very much, Jean. Thank you, Graham. Anyone else want to comment or ask a question?
Yes.
Oh,
Bernard,
go ahead, Bernard.
Can I speak? Hello?
Yeah.
Yes, just a remark on this picture. So I don't remember very well because we wrote something with Virginie Bonali a long time ago, or I don't remember exactly. But just to explain, for example, the picture on the right-hand side. If you consider the half square, the left half square, and you look to on the middle, you look to the Dirichlet condition till the singular point, and the Neumann condition above, and then you look at the family of problems corresponding to Neumann in some part, Dirichlet on the other part in the middle, and Dirichlet outside. Then you get a family depending on a parameter and you can look to the second eigenvalue of this this problem, and there, at least numerically, you observe that there exists a unique T, so where the second eigenvalue is minimal. So we know much better what this picture corresponds to exactly the second eigenfunction of some very specific problem. As far as I remember, I don't remember, I'm not sure if this point was in the middle or not.
So are you saying you're looking at kind of the half square with Neumann conditions here and Dirichlet
here? And then the unknown is the point of intersection. So you get a family of Dirichlet-Neumann problem, and then you minimize the second eigenvalue. And then the minimum should be corresponds to this picture. So in some sense, if you add the assumption that you are looking to symmetric partitions, symmetric with respect to this axis, you have a much more precise analysis.
So you're saying to look at this, kind of look at this flow or evolution that I'm drawing here, just consider it on half of the square, assuming this symmetry.
Exactly.
That's a very good idea, I think.
Yes, we have a paper on this, Virginie Bonailly and maybe Thomas Hoffman also, if I don't remember.
Yeah, thank you. I'll definitely take a look at that.
Thank you. I think there was another question, perhaps from Peter.
Oh, it was not a question. I just want to say that it's beautiful work, wonderfully presented. That's all my complaints.
Thank you very much.
Thank you. Anyone else?
I'll go again. So if you flow in the direction of the second negative eigenfunctions, do you go to some index 1 partition? 3 partition in this case?
I'm not sure what. I'm not sure what would happen in that case. I mean, I haven't thought about that one too carefully, and I mean, you know, in a sense, we haven't actually, you know, thinking about this kind of gradient flow in the space of equipartitions as a way of finding minimal partitions. It's something we're very interested in, but admittedly not something we've really done a lot or really any careful work on at this point yet. It's really just a heuristic picture, and I mean, yeah, I think this is just kind of a cute picture here that if you calculate the eigenfunctions and plot them, it looks like it's moving towards what is conjectured to be the limit. So it's really, there might be something of, I mean, hopefully there's something of substance here, but this is really kind of just a cute observation or cute picture at this point. But yeah, I hadn't thought about where the set deformation along phi2 would, what that would flow to. Certainly an interesting question, though.
Thank you. Anyone else wants to ask a question or make a comment?
I have one sort of fairly general question. So it's about the space of metrics, let's say on the sphere, or maybe, well, actually the space of maybe it's a space of spherical, sort of the model problem is on the space of spherical harmonics, because we know by sort of several works that more or less any nodal topology can be realized by nodal sets. Any possible nodal topology is realized by some kind of spherical harmonics on the sphere, and so we also know in the space of spherical harmonics, generic ones will be like a Uhlenbeck's results. So nodal sets smooth, no intersections, and so on. But this nodal intersection is codimension 1 condition, right? Because the nodal topology has to change. So I was wondering how the nodal deficiency depends on topology, I guess. So it's sort of not so interesting on the sphere, but maybe it's a good sort of test case to understand. And then, but then if you start, so similar things happen in the space of all metrics, where you look at how the nodal partition defined by a given eigenfunction, and you also have like nearby, if you have a smooth thing, then every nodal deficiency and the topology are don't change, are kind of piecewise constant in some sense. But then when you pass through nodal intersections, then it changes. So kind of relationship between the topology of the space of all nodal domains and nodal deficiency. So nodal deficiency is a functional, so how it looks like on the space of all partitions given by eigenfunctions for a given.
Yeah, I think that's a very interesting question, and I mean it's something we've thought about a little bit. I mean, because we have these explicit formulas for nodal deficiency in terms of, say, Dirichlet-to-Neumann maps, and so you can imagine trying to use those to understand, as you deform your domain, say by looking at different linear combinations of spherical harmonics, which cause the nodal domains to intersect and then break apart. As you move through that family, how does the nodal deficiency change? The thing that's tricky about that is, this formula we have for the nodal deficiency in terms of Dirichlet-to-Neumann maps, that doesn't require much smoothness. As long as the nodal domains have Lipschitz boundary, it works. So if there's no intersections, it's fine. If there are intersections, it's fine. So it's valid at every single point in that process. But the thing is, at exactly the time where the intersection occurs, I mean, the nodal domains themselves change. They're either disconnecting or joining together. And so the domain on which this operator is defined changes all of a sudden. So it's a very singular perturbation in a way. So somehow we don't know yet how to use these tools at these kind of singular points. But I think in terms of what I was
So I think
right
for the kind of degeneration that you have in this picture, this is perhaps the nicest possible change of topology you can imagine, right? I mean, just only two nodal lines intersect and things like that.
Yeah, so I think once we understand better how to parameterize these deformations and changes of partitions that alter the topology like this, if we know how to parameterize these better, then I think we would be able to look, say something more concrete about the question you're asking, about giving some quantitative description of what happens to the nodal deficiency when this sort of thing happens.
Thanks.
Now I am getting confused. On one hand, your original Dirichlet-Neumann map approach gave the answer when there are intersections. On the other hand, at the end, you said that Dirichlet-Neumann map doesn't have enough space to accommodate nodal deficiency if there are intersections. How do you reconcile this? I don't. I missed
no, so that's not quite what I said. The thing is, the Dirichlet-to-Neumann map exactly computes the nodal deficiency, even in the case of intersections. And then I said that the Hessian of this equipartition energy generates an operator which is similar to the Dirichlet-to-Neumann map. But basically what we're doing there is, so view the Hessian as a bilinear form on this weighted L2 space, and then closing that form. And so the thing is, when you do that, so you have to enlarge the space to get a closed form. And that's when you're introducing directions, which no longer correspond to smooth deformations. So it's
So this is just in this particular way of realizing the Dirichlet-Neumann map you have problem.
exactly. So those,
Okay.
as far as the Dirichlet-to-Neumann map is concerned, those directions are totally fine. It's when we try to interpret them back in terms of the space of equipartitions, we've somehow left that realm. And that's
Okay. Okay. Thanks.
Thank you, everyone. It's very nice to have a lively discussion like this after talks. Is there anyone else who wants to contribute something? Ask a question or a comment. So thank you very much again, Graham.